Now that we've established our first two equations of equilibrium, we can now move on to the third equation of equilibrium, and that's our moment of force equation. Recall from slides 7 and 8, we ended up with two equations, two expressions, but each of those expressions had two unique unknowns, and so we'll move forward with our third equation that might help to resolve the issue that we had too many unknowns, and those are the moments. And so when we talk about a moment, what we're referring to are those forces that have a tendency for creating a rotation. And to create a rotation, the applied force must have a physical separation from the point of rotation. So with our knee example, the point of rotation is the proximal end of our segment, or the knee joint, and if the force vector has a trajectory that runs through the axis of rotation, its perpendicular distance will be 0. In other words, its moment arm will be 0, so the moment of force it generates will be 0. And so we'll start to account for all of the forces in our diagram that are essentially perpendicular to the long axis of the lower leg, and we'll see that here shortly. So we start in the same manner as we did previously. We have our third equation, and we restate our third equation as the sum of the moments will equal to 0. We'll move the 0 to the left-hand side, and we'll start to lay out our expressions here for all of those forces that have non-zero moment arms. And I have that indicated right here. So we starting on the distal end. We have Fy, which is the force of the elastic band, and we'll take a look at this one right here, 51.3 newtons. And notice that this vector here, sitting on an infinite line of action, that line of action does not go through the axis of rotation, and at a right angle it has a physical separation from it. If we take a look at the 141 Newton force, the 141 component of the elastic band, this force vector sits on its own infinite line of action, and we see that line of action goes right through the joint. So there's no physical separation, hence its moment arm is going to be 0. So the 141 Newton force will not induce a rotation about the knee joint, but the 51.3 Newton force will. And so I have the force of the elastic band in the y direction times its moment arm, and so the perpendicular symbol here indicates that this is the perpendicular distance of the force of the y component of the elastic band. Once we determine that product here, we're going to add that to the product of the next vertical force, which is the weight of the lower leg and foot, times its own moment arm. So how far away is the line of action at a right angle from the point of rotation, or the knee joint? And it's this distance right here. And as we continue to move proximal here, we encounter the force of the patellar tendon in the y direction, and it has a small moment arm, but its moment arm is not 0. So we put the force of the patellar tendon in the y direction times its own moment arm. Now we don't add in the force of the reaction in the y direction because that's going right through the joint, and so it doesn't have a physical separation from the point of rotation. In other words, its moment arm is going to be 0, as will Frx and Fptx, and so all those forces go through the joint, which means that they will not induce a rotation of the leg. Now we've accumulated enough data that we could start to substitute those numbers for our various symbols here, and I'm going to do that. So we have the 51.3, but that's going in the negative direction. So we'll put in negative 51.3. We multiply it by its moment arm, and we're going to put its moment arm at the distal end of the entire system, which is the entire length, which is 0.4 meters. That product will be added to the product of the negative 32.9.2 times its moment arm, which is half of the total length of the lower leg, which is 0.2 meters, and then the force of the patellar tendon in the y direction, which is an unknown. And if you recall on a previous slide, this was one of the unknowns, and so now this will appear in our moment equation, and we know what its moment arm is. It's 0.05 meters. That is the anatomical insertion of the patellar tendon, and even though the moment arm is very small compared to the other moment arms, it's not zero. Therefore, it has the capability of inducing a rotation. So what we do here at this point is I'm going to go take one step forward, and I'm going to carry forward with my calculations. I'm going to find this product, which is negative 20.5 Newton meters, not Newton per meter, but this is a Newton meter because we're multiplying Newton and meter. And we're going to add that to the negative. That's why I just have the negative value here, but we're going to add it to the negative product here of 39.2 times 0.2, which is 7.8 Newton meters. And I'm going to add that to the product of the force of the patellar tendon in the y direction times 0.05. Now this is not given to us, but now we have an equation with only one unknown. So now we can isolate FPTY in this equation, transpose everything to the other side, and we end up with this fraction where we have 20.5 Newton meters plus 7.8 Newton meters. The two negatives become positive when we bring those to the other side. And then we divide both sides by 0.05, and we have a force of 566 newtons generated by the y component of the patellar tendon force. And note that this is a positive value, and that aligns and that agrees with the direction in which the patellar tendon force vector is drawn in our free body diagram. And so the 566 newtons is not FPT, but it's this short vertical component of the patellar tendon force. Now the next step here is to calculate the full patellar tendon force, what we call the resultant patellar tendon force. And I'm just carrying over the value that we had calculated on the previous slide of the y component, which is 556 newtons. So our patellar tendon data includes the insertion, which is 5 centimeters or 0.05 meters from the point of rotation. And recall that we were actually given the angle of insertion, which is 15 degrees from the lower leg. So on the right hand side, this is an expanded view of the proximal part of our free body diagram. It's not the entire free body diagram, but just that part that has the patellar tendon force. And that is angled at 15 degrees, and resolving this into x and y components as we had done before, we have the y component and we have the x component, and the distance from the joint to the y component is 0.05 meters. And so using these data, we'll be able to perform some additional calculations and solve for our x component and eventually get to the full resultant patellar tendon force. And for this, I'm going to use the tangent function, or tan theta, which is equal to the opposite divided by the adjacent length. And so to put this in context to our situation, the angle in question here is 15 degrees from the horizontal of the patellar tendon force, and that's going to be equal to the length of the opposite side. That's the y component, which we had calculated to be 556 newtons, divided by the adjacent length, which is the x component, which is what we don't know. That's what we want to calculate. So We then transpose, move some things around, and we put the 556 newtons, we keep that, and we divide it by the tangent of 15. In solving for this, we find that the x component is 2075 newtons. And that makes sense here geometrically because the angle of the resultant suggests that the horizontal component is much longer than the vertical component. So the patellar tendon force is generating a force that has a greater magnitude in the x direction than it does in the y direction. Now, to use these two data points to calculate the resultant for the patellar tendon, we just use Pythagoras' theorem, and we take the square of the x component, we add that to the square of the y component, substituting those values. I have a typo here. This should be 556, not 552. So make sure you make that change right here. And working through our data here, we have a resultant force of 2,147 newtons being generated through the actual patellar tendon. So this will end this video, but just make one more point here that the 552 should be 556 to correct this typo. And in the next video, we're going to continue with our calculations to determine the reaction force.